So what were we looking at last class? We started looking at the receive architectures. Okay. The first one we started looking at was the direct conversion receiver. And we drew the simplest model of the direct conversion receiver. So you have the antenna followed by some kind of band pass filter, some kind of band select filter. Then you have the LNA. Then after the LNA, you immediately split the system into the I and Q mixers. So in other words, you have one mixer which is driven with the cosine of the LO, and the other mixer is driven with the sine of the LO. And after this, if you need any amplification and filtering and so on, you can put that in here. And any kind of baseband processing, maybe you can convert it to digital and so on. And this will give you the I and Q components of the received signal. This is what we saw last class. And we named the nodes A, B, C and D, correct? And in fact we took into account one more difference. The the sine and cosine could actually, the LO signal could be phase shifted with respect to the input signal, because you really don't know what the relative phases are. At A, the received signal x of t is or let's see at the antenna, the received signal at the antenna is A of t cos omega LOT plus phi of t. At A, you have x of t cos omega naught LOT plus theta. So you just multiply with the cosine. Okay, so this gives you half A of t cos phi of t plus theta plus the 2 omega factor, right? 2 omega LO component. And the minute you low pass filter and so on, this component is gone. Now if you assume that theta is 0, to make our job simpler, we will come back to the question of whether theta is really going to be 0 or not, or how you make theta equal to 0. But let's assume theta is not 0 for now. Okay? So at C, you will have half A of t cos phi of t and at D you will have half A of t, minus half A of t sine phi of t. Is that right? And we said if you want to demodulate the signal or retrieve the signal, you could say that you could do root of c square plus d squared. This will give you half A of t So this will help you retrieve the AM component. Okay. And minus tan inverse D by C is phi of t, and this will help you retrieve the PM component. And we also said we need to remember that we need a 4th quadrant tan inverse. Otherwise you will not get a unique representation of the signal in all the 4 quadrants. So now if once you have extracted the signal amplitude and phase, what do you do next? Well, you probably need to go ahead and digitize it, right? You have extracted the amplitude and phase of the signal. You could either do it this way in the analog domain, but you would probably do this in the digital domain, right? There's no use doing this in the analog domain. Many of the modern modulation algorithms are in the digital domain. So you would probably go ahead and digitize at C and D and then apply these algorithms. Okay? So why do we need both I and Q? There may be several reasons. So the first reason is, of course, the I and Q can have independent modulation schemes. Okay? Okay? I and Q can be independently modulated. You have to retrieve both I and Q. There is no other go. Now, the other reason is, let us assume theta is not 0. And this can be the case in any transceiver. And this will be the case in any transceiver. So what happens when theta is not 0? So, let us take an example. We are trying to transmit AM. Pure AM, right? So that is phi of t is 0. Okay? So the received signal is x of t is A of t cos omega LOT. This is the signal you are receiving. This is the signal you actually want to receive and retrieve. So now let us again write the signals at C and D when theta is not 0. So far we have written it, we have written it in a general form, but if you do this at C, you get half A of t cos theta and so at C you get half A of t cos theta. Is that right? Okay. And what do you get at D? Half A of t sin theta. Is that right? Okay. Now what could be the problem? Correct. Exactly. So for example, if theta was 0 and you are trying to monitor only D, then you have just lost all your information, right? Because your amplitude, your received signal is now completely, it's got so much loss that you can't even retrieve it anymore, right? Because sin theta is so small. Or if you are trying to use the C channel, then it could happen when theta is 90 degrees. So this is the problem. So this is the problem. So even if you had only AM, okay, information only in the amplitude, you would prefer to have both channels. So that is what this means. However, there are other ways more modern ways to take care of this problem. Okay, there are ways to take care of this problem in a modern transceiver. Let us look at the third case and then we'll come back to that. Yeah, of course. You could do something like that. Correct. Okay. So let us say you were trying to transmit PM or FM. Okay. So let us take the case of PM. X of t is some A cos omega LO t plus psi of t. So xi of t A cos phi of t and xq of t is A sin phi of t, right? And we have already seen before, if you had access to only one of these, can you retrieve the signal uniquely? You can't, because you need access to both these channels to actually get a true 4-quadrant representation. Is that clear? You cannot just use one of these signals and retrieve a unique signal. Okay, so let us say you have a modern receiver and you have a phase shift theta between the LO and the RF. Does it cause a problem? Or not? No problem. Okay, so he says no problem. If theta is 90, correct. Okay. So what is an angle between? Suppose I have an angle theta, any angle theta. What does it do to your signal? Huh? It's additive to the phase of the signal. So of course it is doing something. It is not that it doesn't do anything. So it is obviously a problem. It is rotating your signal in some fashion, right? Whatever signal you had, it is now rotated by theta. If I had in fact, if you look at let us say the modulation scheme, so let us say I took the simplest case. So what is going to happen is this whole constellation is going to get rotated by theta. Is it going to affect your received signal or not? It is, right? Or you might have some other modulation scheme, maybe. Something like this. Maybe you are interested in these 4 points. Okay? But now what you are getting is this. Does it even look the same? Looks totally different, right? So how do you solve this problem? Carrier? Recover the phase of the carrier. Okay. So okay, maybe that is one way to do it. Any other ideas? Yes. So that is how it is usually tackled. You usually transmit a pilot symbol, and which you already know, and based on the phase of the received pilot symbol, you then shift the phase of everything else that you receive after that. Is that clear? So that is the easiest way of taking care of this kind of phase shift, because this is actually a fixed phase shift. So the nice thing about this is that this is a fixed phase shift, because the transmit phase, well, okay, it is the received phase is fixed, the transmit phase is not. For the duration of the frame, the transmit phase can be assumed to be constant. Obviously, you will need, for every frame, you will need a pilot symbol from which you will need to detect this. What if you had a small frequency error? So, in other words, what I mean is, you expected to demodulate at a particular frequency, right? You expected the carrier to be at a particular carrier to be at a particular frequency, but it's not. In other words, you thought you were receiving omega LO, you are mixing it with omega LO and taking it to baseband, but you are actually taking it to some, maybe half a hertz or 1 hertz. Actually, that's a lot. Yeah. Correct. You will get a periodically varying phase. So how do you take care of that? Okay. So what you are saying is find the rate of change of okay. So maybe that is one way to do it, but what is the effect of something like this? What is the effect of having a frequency error? Correct. Signal will be modulated by this error. Okay. Anything else? So what to, okay, apart from this modulation, right, there is one more layer between the specific modulation scheme you use and the higher level signal, which you are transmitting. What is that layer? I think all of you probably have heard about it. I don't know if you will be able to relate it to this case. So let us take the case. Maybe you're using some kind of modulation scheme QPSK or QAM, right? Do you just take that signal and then directly take a so let us say you have that modulation scheme, right? Now people say that they talk about a 20 megahertz wideband signal. What do they mean? Okay, correct. But what is the modern way of doing it? Or the last, like I would say 7 or 8 years, have you heard of OFDM? Orthogonal frequency division multiplexing. So what they do is, they split it up into a whole number of subcarriers. This 20 megahertz wide chunk, they split it up into a whole bunch of subcarriers. Each of these subcarriers might be carrying maybe a QPSK or a QAM or something else, right? Now what happens is, you have to preserve each of these subcarriers very, very carefully. If you have any mixing between these subcarriers, it will completely destroy your data rate, right? In other words, obviously when you say orthogonal frequency division multiplexing, you expect the subcarriers to be orthogonal to each other. If they are not, you have a problem. Okay. Now, as it so happens, if you have any kind of frequency error or a certain amount of frequency error, you will end up mixing up these subcarriers badly. Okay, you really cannot afford to have a lot of frequency error, and normally the frequency error specifications are very, very strict. You will see errors of the order of 0.1 parts per million. Okay, 0.1 part per million is extremely tight. So what I mean is, if you have let us say a 20 megahertz reference, right? So you're talking about 2 hertz is 1 part per million. So you're talking about 0.2 hertz in a 20 megahertz clock. Okay, so it's extremely tight. So to take care of this, people have obviously come up with many different ways. The first thing you need to do is to get a very good crystal, obviously. Apart from that, you have to go ahead and compensate that crystal to make sure it doesn't change over time and change over temperature. Okay, and it's very repeatable. So all of these things will have to be guaranteed on both sides. Okay, so obviously both phase and frequency error are a problem. Now part of the frequency error can also be taken into account, not through a pilot signal, but through something called a preamble in the signals. But you can take care of it through coding also. Just wanted to let you know. Okay, so coming back to our receiver. So the direct conversion receiver is very nice. It has a whole bunch of advantages. Obviously, it is the simplest receiver architecture you can think of. Do all of you remember the image problem? So, does the direct conversion receiver have the image problem? No, it doesn't. Okay. Now, apart from being simple, simple also means easy to integrate, because you don't have a whole bunch of components. That also ties in with some of what we have said before. When we say no image problem, that means you don't need an image reject filter. Again, easily integrable. The second thing is, if you have an off-chip image reject filter, you will have to drive an off-chip component. You will have to drive 50 ohms, lots of power. Again, a problem. Okay. No 50 ohm drive. What kind of filtering, post filtering do you need? Or what kind of post processing do you need? The components you get at the output are, the desired frequency, the baseband signal, and the second harmonic. Second harmonic is going to be very far away. Filtering is very easy. Okay, filtering is quite easy. How about the analog to digital conversion? Pretty straightforward. You're just operating directly on the baseband signal. And finally, this is also important, you only have to generate one single frequency, one single LO frequency. You only need one PLL. Okay, so all of these are very nice things about the direct conversion receiver. Unfortunately, it also has a whole bunch of problems. Well, a couple of problems. Let's not say a whole bunch, because we are going to concentrate on this, so I don't want to say a whole bunch, right? So any ideas as to what the disadvantages could be? Huh? 1 by F noise, very good. Okay. 1 by F noise of what and where? Does the 1 over F noise of the LNA matter? LNA doesn't matter. Does the 1 over F noise of the mixer matter? Okay. So, which means that you need to be careful when you can't just say blanket 1 over F noise. When you say 1 over F noise, you need to specify what the 1 over F noise of which blocks matter. So, obviously 1 over F noise of the mixer will matter. Okay. Not will matter. It could matter. But definitely 1 over F noise of the baseband circuit is what will definitely limit your performance. So, you will need to have very large baseband devices. Okay. Now, this means that you need to have very large devices in the baseband. Okay. Anything else? Correct. The assumption is that when you actually do a super heterodyne kind of receiver, since you have more number of intermediate processing stages, you're also amplifying it correspondingly. Okay. So what happens is the signal is already large enough at that point where you don't need to use very large devices. Because really here in this case you're getting gain primarily only from the LNA, maybe a little bit from a mixer. Okay. Any other issues? Similar to 1 over F noise. DC offset, okay. Okay. So DC offset could be a problem, right? Just like 1 over F noise. If you have your amplifiers downstream will have input referred DC offset and they could end up limiting your performance. For example, if this DC offset was a time varying DC offset, you could actually damage part of your received signal itself. Any other kind of DC offset you can think of that could cause a problem? Obviously the inherent DC offsets of the amplifiers themselves are a problem, but I think the solution is the same. You have large devices that will give you better matching and it will give you better DC offset also. Solution for 1 over F noise and DC offset are similar, right? But can anything else give you something which looks like a DC offset? We have seen this before. Feed through from the LO port to the RF port could actually give you so if you actually have feed through I'll just draw it in a different color. So if you actually have feed through from the LO port to the RF port, you will end up getting a DC offset. Okay, this is called LO self-mixing. So this is obviously another problem. So I'll call it number 3. Anything else? Well, the minute you say LO leakage, LO self-mixing, you can think of multiple other cases also. So for example, I have an interferer leaks from the RF port to the LO port and then mixed together to give you a DC offset. You can think of something like that. Okay. Something like this or something like this is also possible. Okay, this is the interferer leakage, this is LO self mixing. Anything else? LO pulling. So this is not I would say this is not a very common problem. We have seen that it's a problem in transmitters. Now in receivers, obviously if you get too close to the transmitter, your received RF signal can become large enough to pull your LO. It's not a very common problem, but it is definitely possible. What else? We have seen one more problem associated with direct conversion receivers. We saw it in the case of mixers. Sure, but if there is direct RF feed through, it can be very easily filtered, right? Good. Correct. So yeah, so that is what I was leading to, which is even order distortion is a problem. We have seen this when we studied mixers, and let us say you have the LNA driving the mixer. I will call these three nodes A, B and C. Now, apart from your desired signal, if you actually have two large interferers, so this is my desired signal. And apart from that, I have two large interferers at some omega 1 and omega 2. Okay, so if you have even order distortion in the receive path, what happens is maybe at B, so this is at A, okay. At B, I now have a component at omega 1 minus omega 2, apart from my omega RF, omega 1 and omega 2. Now, of course, these guys, this can actually cause a problem. We have already seen this before, so I probably won't dwell on that. Anything else? Okay, now we are really grasping at straws, right? Trying to find out something wrong with the system. But really the biggest problem is the DC offset problem. Whether it's caused by self-mixing, interferer leakage, or something else, that is really the biggest problem. Now the DC offset can also be time varying. So But you should realize that this is actually a very big problem. It is not a small problem at all, because if the signal you're receiving has an amplitude of let's take a cellular signal. You're trying to receive a signal which may be smaller than a microvolt, right? Maybe the LNA gain is 20 dB. 20 dB is let's say the voltage gain is 20 dB, so it's a gain of 10. So you take it up to 10 microvolts, right? And it goes through a mixer, and let's say the mixer also has a gain of 10, so that's 100 microvolts. The typical, input referred DC offset of an amplifier may be in the several millivolts, if not tens of millivolts, right? So it is not a small problem. It is definitely not a small problem at all. The thing is, we have actually managed to solve it because of the signal processing power we have, which is we are actually able to calibrate out the DC offset. We're able to measure it ahead of time, calibrate it out, and then we can go ahead and apply the DC offset correction and then go on with life as usual, right? That is the only reason why we have actually been able to use the direct conversion receiver with most of these modern receivers. Otherwise, we wouldn't have been able to. If you go even maybe 10 years ago, 10 years ago, there were still people looking at many other architectures, whether it is heterodyne receivers, or there are other things called very low IF receivers, VLIF, but now it's becoming less and less common, primarily because this is just so much simpler, and you can take care of these problems. Offset correction, DC offset correction has just become so commonplace that you don't have to worry about it at all. Is that clear? Okay, so apart from this, after this you have to go ahead and do analog to digital conversion after you do this gain and filtering, and normally if you had to retrieve the channel from the band, you would probably do it in the digital domain. You really don't have you don't gain anything in doing it in the analog domain, so you go ahead and do it in the digital domain. Obviously the ADC will have to take care of the dynamic range of the your received signal versus whatever other received signal is there in the other channels, right? Apart from that, everything else is similar between the heterodyne and the direct conversion. So let's stop here, and so tomorrow morning, when is the class? Is there a slot swap?